In this lesson, we're going to discuss the effect of curvature on beams with moments applied. So first, let's review the assumptions. The assumptions listed are for straight beams. So we're going to consider we're not going to consider the segments that are directly next to or near the applied loads. We're going to assume the beam is loaded in the plane of symmetry. We're going to assume that the cross sections that we take are in a plane perpendicular to the neutral axis. We're going to assume the material is homogeneous and obeys Hooke's law. We're going to assume the stresses are not great enough to cause elastic deformation, and that the deformations that we see will be small. The stresses are still in the elastic region. We won't see any plastic deformation. The segment has pure bending, and the only assumption we're going to relax is now we're not going to say that the beam is initially straight. So let's take a look at a beam. This particular one has a rectangular cross section, but we'll generalize it shortly. And what we're going to notice is that the centroidal axis has to do with the geometry, what is in the center of the geometry. The neutral axis is defined as the place along the axis in which there are no stresses. So for a straight beam, the neutral axis lines up on the centroidal axis and everything is okay. But for a curved beam, we notice that the stress distribution now still has a compressive component on the top of the beam and a tensile component on the bottom of the beam, but the center of the beam is no longer at zero, and there exists this neutral axis where the stress is zero. We should also notice that the stress is no longer in a straight line. It now has a hyperbolic shape rather than a linear shape, and that the stress at the inner surface appears to be greater than the stress at the outer surface, and that's going to be typical of curved beams. So there's a couple definitions we need to see. The biggest one is the distance that we're going to call E that the neutral axis has moved from the centroidal axis. And the strict definition of that is RC is the distance from the radius of curvature of the centroid. Okay, so this is how curved the beam is. That's what RC is. And we're going to subtract the area over the integral of dA over R. Okay, and that's going to tell us what the actual distance is. Well, this is obviously quite mathematical, but for common shapes, Shigley's machine design book lists several RC and RN values. So now it's just a simple matter of calculating what E is from this table. Okay. So a couple things to notice, and we'll notice on the going back diagram as well. Ri is the radius from the center of curvature to the inside of the beam. Ro is to the outside of the beam. RC is to the centroid. And then you have these values. Ci is the distance from the neutral axis to the outside. CO is the distance from the neutral axis to the outside. And again, E is the distance between the centroidal axis and the neutral axis. Rn is the distance from the center to the neutral axis. That should cover all of our definitions. So now, using this table as a guide for when we have things like I-beams or circles or rectangles or whatever shape that we have, we can consider a curved beam. So in this case being shown, the curved beam only experiences a moment. Okay, so there's a moment that's twisting the edges of the beam, causing a pure moment stress inside the curved part of the beam. And what we're going to do now is we're going to say that the inside stress is equal to M times E. We know how to calculate E. A, we know what the cross-sectional area is. r is the radius to the inside, and then ci is the distance from the neutral axis to the outside. Okay, so this becomes our new equation for finding stress, for finding the maximum stress. So we should expect that sigma I will be the greatest of the stresses that the beam experiences, and we should expect that the outside will be in compression. There's a minus sign there. There's a lot of cases where instead of a bending moment being applied, we can actually have two forces, for instance, a hook or something like that. So this is a fairly common analysis, and looking at this analysis, it's now become a combined loading. So we have a moment that's induced. If you were to do a free body diagram across the interior right here where this break occurs, you would recognize there has to be a moment that counteracts the moment that's created by this force times the distance away that this is. But there's also an axial load. And so here's the free body diagram of it broken in half with the internal moment. We can calculate what that moment is. Again, it's going to be this force times the distance away that the force is. And now we have the same term for the stress. So this M is still producing a stress caused by the moment, but we also have F over A as well. So this is again a combined loading situation. In this particular loading situation, there is no transverse shear forces, and there's no twisting forces that would be rotating the hook the other direction, so out of into the page, or maybe around the F. So there's no torsion occurring. So in both of these cases, if those other cases existed, we would have to check the full stress state. As it is, this will suffice for the stress state that's occurring on the inside edge of that break and on the outside edge of the break, looking at these two. And there would not be any other stresses in any of the other directions. No other normal stresses, nor any other shear stresses. So these will define our stress state at those locations.